Hello students and welcome to Chemistry B. I'm Miss Slate and today we're going to talk about the ideal gas law. So we've already talked about how some different factors affect how gases behave, mainly temperature, pressure, volume, and literally the amount of gas that's present, which we typically deal with in terms of moles. The ideal gas law allows us to relate all of these factors together via the ideal gas law constant. So the ideal gas law is PV equals nRT, meaning pressure times volume is equal to the number of moles times the ideal gas law constant times temperature. And just like before, anytime we're dealing with temperature, we are going to need to be dealing with temperature in Kelvin. There are three different constants for the ideal gas law because they are slightly different depending on what pressure unit you are using. The gas law constant will always be given to you on problems and tests and quizzes, though. So let's look at an example. Our example says calculate the number of moles of gas contained in a 3-liter vessel at 3 times 10 to the second Kelvin with a pressure of 1.5 atmospheres. Well, again, we're going to solve this using the guess method. So starting by noting what our givens are. So they tell us our volume is 3.0 liters. They tell us our temperature is 3.00 times 10 to the second Kelvin. And they tell us our pressure is 1.50 atmospheres. Our unknown in this case is the number of moles. That's what they're asking us to find. So next up is the equation. Which our ideal gas law equation is PV equals nRT. Now, just like usual, you could at this point immediately go to substitute and solve, or you can rearrange the equation to solve for what you want. I like to rearrange the equation beforehand, so that's what I'm going to do here. So I'm going to rearrange this equation to solve for n, which I can do that by just dividing both sides by RT. So pressure times volume divided by the ideal gas law constant times temperature. And then our last step is, of course, just substitute and solve. At this point, we need to make sure that we select the correct gas law constant. Our pressure is in units of atmospheres in this problem. So we need this first constant, the 0.0821 liters times atmospheres per mole Kelvin. And we get an answer of 0.18 moles of gas. We're rounding to two significant figures because we are multiplying and dividing, and our lowest total sig figs is 2 from the 3.0. Let's look at another example. So this one says how many grams of gas are present in a sample that has a molar mass of 70 grams per mole and occupies a 2-liter container at 117 kilopascals and 35.1 degrees Celsius. Well, just like always, the first thing to do is to identify what the given information is. So first off, they tell us molar mass. And they also tell us volume. And they tell us our pressure. and they tell us our temperature, which I'm going to convert to Kelvin right away. And then our unknown is mass. Now, right off the bat, this seems a little confusing, right? Because mass isn't a part of our ideal gas law equation. However, when you encounter a problem that you don't immediately know how to solve, you should start by doing the things that you do know how to do. So for example, I know if I have volume, pressure, and temperature, I can solve for the number of moles. So that's the first thing I'm going to do. Once again, at this point, we need to make sure we're selecting the correct ideal gas constant. This time, our pressure is in units of kilopascals. So the constant that we need to use is 8.31. And at this point, we get 0.0914 moles. Now, this isn't our final answer, though, because what they really want us to do is mass. Now, here's the easy thing, though. They gave us the molar mass. If we have moles and we have molar mass, we can use some basic stoichiometry to convert to mass. Because according to the molar mass, there is 70.0 grams of this substance in 1 mole. Which means the mass of gas that's present in this problem is 6.40 grams, roughly. And this is how we see that stoichiometry can be very closely related to our gas law problems. And we're going to be getting more in depth into how the gas laws relate to stoichiometry in our next lesson.